Hello everyone. We will now discuss an interesting topic of semiconductors, that is Fermi Dirac function. But before we proceed with the semiconductors, we will understand the concept of Fermi Dirac function in reference to metals. We will see what is the Fermi Dirac function, what is the Fermi level in case of metals, and then we will switch over to conductors. So first of all, the Fermi Dirac function is defined as, that is probability. It is basically the probability function. The Fermi Dirac function is defined as the probability of occupying an energy state by an electron. So the probability of occupying this energy state by an electron is given by 1 plus e raised to power e minus ef divided by kT. This is called Fermi Dirac function. Now, important point here is, what is EF? The EF is called, this EF is called Fermi level, that is Fermi energy level, you can say. This is Fermi energy level. And what is K? K is nothing but Boltzmann constants. So this is Boltzmann constant. T is temperature, and that is taken in Kelvin. So these are the different parameters involved for calculation of probability of occupying an energy state by an electron. Here K is basically, that is 1.38 into 10 raised to power minus 23 joules per degree Kelvin. You can just remember, otherwise if you have numerical, it is always given to you. So this is nothing but small k, that is Boltzmann constant. Now at E is equal to EF, if you see the probability of occupying an energy level, that is Fermi level, the probability of occupying is equal to 1 by this EF minus EF becomes 0, so e raised to power 0 is 1, so 1 by 1 plus 1, that is equal to 2, so this is 0.5. So how can I define this EF? Fermi level I can define now. The Fermi level is the energy level where the probability of occupying the energy state is 50%, or we can say the Fermi level is the energy level where the probability of occupying that energy state is 50%. So that is how we define the Fermi level. So this formula will be used again and again, so you should remember this formula, and this is important expression, you should remember it. Remember, this topic is very important for engineering services exam, especially prelims, and there can be question in mains as well. Engineering services mains, as far as GATE is concerned, you can have question, but there are very few questions which have appeared from Fermi level in GATE, but there were. You cannot neglect the topic from GATE point of view as well. Now, after Fermi Dirac function, we will discuss very important concept, and this concept is not very much clear to most of the students. That is known as the density of states. Density of states. This is very important concept. Normally we define it NE, that is density of states. So before you proceed with this, we will talk about the energy density function. Energy, rather than saying energy density or energy distribution, sometimes it is called energy distribution function. Sometimes it is called effective density of states. So before we talk about this, let us talk about energy density function, that is density of states. Normally that is denoted by this expression rho, in that is subscript, it is E. Rho E is equal to Fe, that is Fermi Dirac function, into Ne, where rho E is energy distribution function or effective density of states. This Ne is called density of states. So N as a function of E is called density of states, or you can say this is possible, maximum possible, you can say possible, maximum possible density of states. Density of states. Let us understand the physical interpretation, physical meaning of all these three parameters. This is important to understand because we will be switching over to semiconductors, and if you don't understand this, it will be difficult to understand the semiconductor part. Suppose you have a metal, and this is the Fermi level in the metal. This is Fermi level, this is energy state, and this is your energy. Sometimes you call it as wave function, or you can say this is a distance x. So now suppose you take small volume, of the metal. The energy of this is varying from E to delta E, that is E to E plus del E. E to E plus del E. Now this rho E is basically, let us talk about this first. This Ne is nothing but, remember, Ne is nothing but number of possible, you can say maximum number of electrons. I repeat, N is maximum number of electrons per unit electron volt, or per electron volt kahiye, per electron volt of the energy per unit volume, The meaning is, let us understand the meaning now. Maximum number of electrons per electron volt per unit volume, that is Ne. I am taking this small portions. Just visualize, you need to visualize the three-dimensional space inside the metal. And if you take certain energy level from E to delta E, so what is this gap? This variation, this is change in energy delta E. So you can just consider just like this duster, you are considering some space inside the duster. Say this is the metallic block. So inside that block, if you shift from one level to another level, although there are no discrete level, we have the bands of energy. So if you have small band of energy at certain distance from the atoms, where energy is basically varying from E to delta E, E to E plus delta E, that band of energy is dE, you can say, rather than saying delta. So in this band of energy, in this space, basically energy is varying at every point. So you are considering small space in the metal. In that space, how many possible electrons can be there? Those many electrons per unit volume divided by that energy band, number of electrons in this volume divided by the volume of this space and divided by the energy band of that volume, that is nothing but maximum possible states. We are assuming every energy state is being occupied by the electron. So Ne is maximum number of electrons per unit volume per unit energy of the particular band, particular space in the metal. That is nothing but maximum density of states. Now let us talk about the effective density of states. Sometimes we call it as energy distribution. So this effective density of states is nothing but, this is called number of electrons, not maximum. actual number of, you can say, I'll say actual number of electrons per electron volt of energy per unit volume. Let us understand the meaning of this again. Here it was maximum possible. I just try to understand. In case of metals, all the electrons are free. When all the electrons are free, so it is may not be necessary that if this particular level of energy is occupied. Why? Because electron is movable, that is moving continuously. There is maybe possibility that electron is there or it may not be there. Or I'll say there is probability, some probability that electron is there. That probability is given by this function, Fermi Dirac function. Fermi Dirac function says whether a particular energy level is occupied by the electron is given by this function, Fermi Dirac function. So if I multiply the maximum possible states, energy states in this volume by the Fermi Dirac function, that will be giving me what? Actual number of electrons in that differential volume. I repeat, maximum possible electrons in that particular volume per unit energy multiplied by Fermi Dirac function, that is probability of occupying those energy states, is nothing but effective density of states, means actual number of states in that particular volume per unit energy. That is nothing but your actual density of states. So you should understand the meaning. Now suppose I have to find the number of electrons. So I hope you will understand, you will remember this formula. Now suppose you want to find the number of electrons in that differential volume. So I'll say number of electrons in energy band E2 E plus DE. I want to find how many electrons are there in this volume. So understand again, rho E is what? Actual number of electrons per unit volume and per unit energy. So if you want to find out the number of electrons in this differential volume, or I'll say that is nothing but Dn, that is basically electron density. It's not basically this and a number of electrons in energy band per unit volume, I'll say per unit volume. So that is nothing but rho E multiplied by dE. This Dn, n is what? Number of electrons per unit volume. Understand the concept? I have the actual density of states. Actual density of states are what? That is number of electrons per unit volume per unit energy. Now I want to find the number of electrons per unit volume in this. That is nothing but electron density. So to find the electron density in this volume, in this energy band, I simply multiply this rho E by dE. So that is nothing but this is what? Number of electrons per unit volume per unit energy, multiply it by energy band, so it becomes number of electrons per unit. This is another concept I may be using. So now for metals, remember this, for metals the maximum density of states, for in case of metals the maximum density of states is given by gamma into e raised to power 1 by 2. This is the formula you should remember. For a Fermi level, you should remember this formula. So Ne is maximum possible density of states, means what? Maximum number of electrons per unit volume in this per unit energy band is nothing but Ne. For metals it is given by this, where gamma is nothing but a constant. It has got some value, that is nothing but 6.42 into 10 to the power 27 approximately. This is approximate value. So that is nothing but gamma, are constant. But you don't need to remember this. If you have numerical, that may be given, but there is least possibility, especially in GATE. There can be question in engineering services. Now, if you see this, so what is dn? This implies dn is equal to, I'll rewrite this equation, that is what? Fe into Ne multiplied by de. So this gives d, if you integrate it, that will be equal to n equal to Fe Ne de, and integrate this. This will be your n. Now there is interesting point you should know and you should remember. If you remember the Fermi Dirac function Fe, that was what? 1 by 1 plus e raised to power e minus ef by kt. I will assume absolute 0 at T equal to 0 Kelvin. At T equal to 0 Kelvin means absolute 0. What is the Fermi Dirac function? The Fermi Dirac function Fe is equal to, you put T equal to 0 here, it will become e raised to power infinity. E raised to power infinity is nothing but infinity. If it is infinity, this will be equal to 0. But there is important concept here. It will depend upon this variation. This will be equal to 0 when E is greater than EF. And now this will be equal to 1, in which case if E is less than EF. That's what you have. So the Fermi Dirac function is 0 for E greater than EF. It is 1 if E is less than EF. So it depends upon the whether E is greater than EF or less. If it is greater, it will be infinity. If it is less, it will be 0. So that is how you have. Now at absolute 0, at absolute 0 means what? 0 Kelvin. So at absolute 0, that is nothing but 0 Kelvin. What do we have? See this, the concentration Ne will be equal to integration this 1 into Ne is what? Gamma e raised to power 1 by 2 de. But remember, you are taking E, it means energy is varying from where to where? From 0 to EF. Why? Because it is 1 only for this range. E is less than EF. If E is less than EF means E is varying from 0 to EF. So that is the concentration. So the concentration of electrons is given by this in metal. So that is equal to, gamma can be taken outside. You can integrate it, 1 by 2 plus 1 divided by 1 by 2 plus 1. That is the integration of this. So this gives what? Gamma e raised to power 3 by 2 divided by 3 by 2 means what? 2 by 3. So the concentration of electrons, but remember this is what? EF. This is what? EF. So N is equal to 2 gamma EF power 3 by 2. This is the concentration of electrons at which temperature? At 0 Kelvin. And when, just remember this, when temperature is 0 Kelvin, all the electrons are below Fermi level. Why? Because the probability of occupying the energy state below Fermi level is 1. So it means all the electrons are below Fermi level. Probability of occupying an energy state above Fermi level is 0. That means there is no electron above Fermi level. So when there is no electron above the Fermi level, or all the electrons are below the Fermi level, that state is called degenerate and state of the metal. I repeat, what is degenerate state? It is the state of the metal when all electrons are lying below Fermi level. There is no electron above Fermi level. So that is called a degenerate state. So we will discuss that in case of semiconductors as well. Now I can write, suppose here this is the concentration of electrons, and if you have to find this Fermi level, so I can say Fermi level at 0K is nothing but EF is equal to, you can write 3 by 2 n by gamma power 2 by 3. This is the Fermi level in case of metals. I repeat, this is to make you understand the concept of Fermi Dirac function, density of states, the concentration of electrons, and Fermi level in case of metals. I hope the concept is clear. Just a review. Maximum density of states is what? The maximum possible electrons per unit volume per unit energy in the metal is maximum density of states. Sometimes we call it simply density of states. Then energy distribution function, that is nothing but effective density of states, that is equal to the actual number of electrons per unit volume per unit energy, that is effective density of states. So the effective density of states is equal to what? The Fermi Dirac function into maximum possible density of states, that is actual density of states, and from there we derive these expressions. So this is nothing but Fermi level in case of metals. So I hope the concept is clear. After this we will talk about the Fermi Dirac function, the Fermi level, the concentration of charge carriers or electrons and holes in case of semiconductors. So but I won't be taking you to the much longer time. Reason being, the video will become lengthy, so I'll be discussing that concept in separate video. So for the time being, just understand this concept. Thank you.